So we'll start in a minute, if that's okay.
Yeah,
that's perfect. Wonderful.
In a minute. Give me just 2 minutes time.
Okay. So we'll start in a minute, if that's okay.
Yeah.
Wonderful.
Give me just 2 minutes time.
Okay.
So good evening, everyone, and welcome to the last session of day 1 of ICSFA 2020. This is a symposium on Ramanujan's work, on the works of Ramanujan, and we have some eminent speakers in this symposium. And this session will be chaired by Professor Atul Dixit, who is at Indian Institute of Technology, Gandhinagar. So may I request Professor Atul to chair this session.
Sure. Thank you very much. Thank you very much, Professor Ali. And very good evening to all of you. We'll be starting the talks in the symposium on the works of Ramanujan now. Our first talk will be given by Professor Peter Paule, who is at Johannes Kepler University, Linz, and also at RISC, that is the Research Institute for Symbolic Computation. And Peter will be talking on Ramanujan holonomic sequences and modular forms. Over to you, Peter.
Thank you very much, Atul. Can you hear me?
Yes, I can.
So thanks not only to you, also to Professor Ahmad Ali and your colleagues on the organizational board here. It's just wonderful. It's a big pleasure to speak at the occasion of your symposium on the works of Ramanujan. And it's not only a pleasure, it's really an honor to be on board here. So thank you for inviting me.
Thank you.
What I'm going to tell you is a story connecting holonomic sequences. These are sequences satisfying a linear recursion with polynomial coefficients with modular forms. And the story will be connected strongly. So this is the symposium is on the works of Ramanujan. The story will have several connections to Ramanujan. And what I'm going to tell you is joint work. Actually, it's quite recent work with Silvio Radu, a collaborator of mine. I hear some noise.
Peter, can you unmute? I think you are muted. Peter?
I think he is muted.
Yeah.
Yeah, he is stopped.
Yeah. Peter, you are muted. Yeah.
Okay. I see, but I didn't do anything. So
yeah.
Please let me know in case you don't hear me anymore.
Sure.
So I start sharing again, okay?
Yeah.
Maybe. Can you hear me?
Yes.
Yes. Okay. So concerning the modular background, so what we use here is the modular group and subgroups. And you see here an entry from the special linear group. This entry here is coming with constraints where there's some divisibility constraints on A, B, C, and D. The determinant, this is all integers, this A, B, C, D, and the determinant is 1. So the well-known subgroups, the gamma 0 is there, the gamma 1 is there, the gamma n is there. The details don't count, but the modular, the action of the group to produce the symmetry of modular function and form objects is done by elements of groups of this kind. Throughout my talk, we have the Q fixed to e to the 2 pi I tau, tau from the upper half of the complex plane. The action I already mentioned is on the upper half plane in this standard fashion, and you will see the Dedekind eta function arising frequently in this talk. Already at the beginning of this introductory example, we have it here. Recall the Jacobi theta functions, theta 2 and theta 3, and we use them for setting up the main theme of my talk. For proving and for utilizing the modularity, I mentioned, not in detail, just on fly, that these two objects, when I square the first Jacobi, the theta 2, I get this relation. When I square the theta 3, we get the same relation here, but with respect to different groups. The details don't matter. Just keep in mind the symmetry is here of a modular form symmetry with weight 1, because this arises with exponent 1. So I mentioned there's one major theme here in, guiding the whole talk. There's given a modular form, we call this modular form G in most of the examples. Given a modular function, this means the weight here is 0. Here in this particular context, the expansion at infinity is not in Q, but it's in X, where the X is defined like this. And our task throughout this talk will be the following: fixing the G and the H. We try to expand locally the G in terms of the modular function, so the modular form G in terms of a series, a power series in the given modular function H, and we want to determine the coefficients. This is a classical theme that, according to Ja Yee, traces back to Gauss and Felix Klein and others. Very classical theme. Here, let me also mention that the H is fixed in a way we use the fourth power of the elements theta 2 and theta 3. So it gives us actually the modular invariant lambda. Here we normalize because we want to start in this fashion. So I normalize with the 2 to the 4. So what can we do to solve our problem? First of all, first remark, these coefficients can be computed very easily. Here you see, I don't go into details, but here you see what you do in Mathematica. When you start Mathematica, you can do the same in Maple. You get the first coefficients in this easy fashion. So the C0 is this, the C1 is this, the C2 is this. So it's all produced in a few keystrokes sitting in front of your favorite computer algebra system. Of course, producing the coefficients, this is not proving anything about the coefficients themselves. So let us first, before we go to proving, let us first conjecture structure on these coefficients. And here, if you would do this problem yourself, either you know or you find out very quickly that the structure is extremely simple for this CK and elegant. So here I don't use human insight. Here I just use a package that has been produced here in my group. We find that we guess for this CKs here, we guess in inserting a string of the first 12 elements of the sequence, we guess that this sequence is satisfying a recurrence of order 1. This is an automatic guess. Here I just repeated the sequence, and if you, this is order 1, if you want the CK in closed form, if you prefer binomials, the CK is just the central binomial taken to the square, or in hypergeometric notation, if you use the rising factorial notation, it's written in this form. I prefer for this purpose to refer to the hypergeometric series notation. So in other words, what we conjectured is that the given modular form, when locally expanded in the powers of H, produces these coefficients in front, or in hypergeometric notation, if I rewrite this series in hypergeometric notation, a 2f1 in the parameters 1/2, 1/2, bottom parameter 1, and argument lambda. So the next task, so this is a guess. My first point is we can, by simple computation and computer-assisted guessing, we can come up with such a conjecture. Of course, we desire to prove, once we have such a conjecture in hand, we want to prove it. And to prove this, and this is so to say the second main message in this talk, proving this also can be done algorithmically. And to this end, in order to do so, we convert the conjectured recurrence into a differential equation. Namely, so we have this recursion on the coefficients, on the CK, and denote, so this is the guessed closed form here for the CK, denote this series expansion by YZ. So if you plug in the H here instead of the Z, you get this function back. And we want, for this power series, we want a differential equation. Also, this can be done automatically because of the fact that this CK is holonomic. It satisfies a recurrence that is linear with polynomial coefficients. And elementary theory tells you, if you take as a coefficient sequence such a holonomic sequence, the generating function is satisfying a differential equation of holonomic type. This means, so it's an intimidating word, but it's very simple in its meaning. It's again linear, it's satisfying a linear differential equation, and again with polynomial coefficients. So you see here the coefficients of the differential equations satisfied by the y is polynomials in Z. As a side remark, you can go both ways if you have a differential equation. So here we went from the recurrence to the differential equation. You can go backwards. You use you take as input the differential equation. You do the differential equation to recurrence equation, and you are back at the recurrence equation we have started. So it's both ways. Recurrences for the coefficients of the generating functions correspond to differential equations on the full object on the generating function, and vice versa. Let me again, since it's the main point of the whole talk, in order to study expansions of this kind, we first conjecture, computer-assisted, a recurrence for the coefficients. We turn this recurrence into a differential equation. Now, look, I don't take this differential equation in Z, but in H, because we work locally, so the expansion in H should hold in a reasonable analytic context. And my message is this: if I am able to prove that for the given, maybe I show you that this information is using the full information we started with. So the y in H is nothing but the G that is given. It's the modular form. The y, the derivative of y in H is, this is here, by the chain rule, it's the quotient of the given G derivative and the given H in its derivative in tau. So this differential equation is using the given data. And if you are able to prove this differential equation, you prove the whole expansion, because the differential equation gives you the recurrence equation and gives you the whole story on this expansion. And now you might say, I move from something very, very, very elementary, the recurrence, to something more intriguing, the differential equation. What do I gain? And now this is the next point I want to make. You gain a lot. Namely, there is an algorithm that I spelled out recently with Silvio. So Silvio rather was an essential engine here, as in many recent work I was involved with. So we designed an algorithm to prove automatically correctness of differential equations of this type, connecting differential equations that connect a modular form with a here G with a modular function H. So in other words, this can be proven algorithmically. Sorry for scrolling back. Also, this relation then is proven algorithmically. So it's discovered algorithmically once you fix the modular form, and the H you want to expand with. You get the guess on the CK. You transfer the problem to proving a differential equation, and the proof of the correctness of the differential equation can be done using the algorithm mod form, DE, as we called it. Our work is based in essential ways on work by Yifan Yang. You'll find, if you are interested, you'll find this in 2 recent papers. You'll find the detailed descriptions of applications that I'm going to tell you today, and the underlying structure of the algorithm. I don't have time for today to go into the details of the algorithm. The principle is that we convert this differential equation in Yifan Yang form. This means we use generators Yang came up with. These generators are linearly independent. The translation of this differential equation into this vector space language is such that the coefficients that arise are modular functions. And in order to prove correctness, we have to do zero recognition of these modular function coefficients. This is the principle in a nutshell. But as I said, I don't have time to tell you more details. Finishing on this introductory example, let me mention that this is strongly related to Ramanujan. It's entry 6 of chapter 17, page 101 in Bruce Burns' part 3 of Ramanujan's notebooks. And as mentioned by Bruce Burns, it's one of the central theorems in the theory of elliptic functions, because once you have this, you can easily prove that this is nothing but when you expand this integrand and you integrate from 0 to pi squared, to pi divided by 2, you get the complete elliptic integral that's often abbreviated in this way. And this k is the modulus. When you square it, that's arising here squared, you get the lambda from this argument. So what I have shown you in the introductory example, I have shown you a computer-assisted discovery and proof of a key fact in elliptic functions. Before I present you further examples, very much in brief, the general connection again, connection between a given modular form, a given modular function. We are interested in expansion of this kind. We guess a recurrence equation. We translate this recurrence equation into a differential equation, which is still guessed. But finally, we prove the differential equation algorithmically and have then a full proof of the corresponding relation. There is a special case of the whole setting where the modular form has weight 0, so where the G has weight 0, then we call it the modular function. In this case, we don't need to go to a differential equation. We can stay with an algebraic equation, which makes things not less interesting, but simpler in its mathematics. There is another aspect I want to mention very briefly. Before we had the H here, and in standard expansions, the order of H is 1 to enable to admit such an expansion. However, if the order of your given, you might be interested in connections with a modular function of higher order, or I'm speaking of the Paule order, so if the order is a negative number, you can renormalize it in a way that the expansion function is of order 1, and you get relations of the same type, whereas in contrast to what we looked at, the connection to a modular function is of a higher order type. Still possible, which is based on the fact that a differential equation having, I mentioned this very briefly, a differential equation linear with algebraic function coefficients can be translated in a differential equation where the coefficients are only polynomial. This makes, in principle, this extension possible. Let me briefly cite Ja Yee. Ja Yee says this setting is at the heart of the original discovery of modular forms by Gauss. He says this in his big survey in the book 1, 2, 3 of modular forms. He points to Fricke and Klein, and he gives the statement in this form. This is just cited from Ja Yee's article. G, a modular function of positive weight, H, a modular function, as I showed you, both with respect to a given congruence subgroup. We express G locally as what we had as a series in H, and the name of the series is Y. then the function, we now consider the series plugged in back with the H, satisfies a linear differential equation. We even know its order. It's k plus 1 if the weight is k. And Ja Yee says with the differential equation has algebraic coefficients or polynomial coefficients, provided the underlying Riemann surface has genus 0 and the order of H is 1. What I told you already is actually saying that the restriction to genus 0 and to order 1 is not necessary. You can extend this, you can relax. You get a differential equation with polynomial coefficients in all instances, even if the genus is not 0, even if the order is not 1. There is a price to pay. In contrast to the algebraic coefficient setting, the corresponding holonomic differential equation might have an order greater than k plus 1. So I have to be fast on this, despite, so Ja Yee says this is folklore, but as Yi-Fan Yang pointed out, so this is also what I found, maybe there are experts in the audience who know better, that the first nailed down proof in modern language has been done by Peter Stiller in the mid of the 80s. Ja Yee, being very much enthusiastic about this connection, gives 3 proofs. His third proof is constructive. This means given the modular function, modular form and the modular function H, it constructs the associated differential equation. Our approach is different. We first guess the differential equation and then prove the guess differential equation. It's so to say coming just from the other direction. I don't have time to dive into the aspect of when the G is a holonomic is a modular function. So if it has weight 0, then I told you instead of a differential equation, we are dealing with an algebraic equation. This is related to standard knowledge in Riemann surface theory, but I see that time is flowing, so let me skip over these remarks. I have inserted a few propositions here that are relevant for algorithmics, but not relevant for the talk. Instead of going into details here, let me show you examples. It's a Ramanujan workshop, so I would like to start with Ramanujan. There's a very nice survey paper by Barua, Bruce Berndt, and Henghua Chan in the monthly 2009, where they mentioned that all 17 series Ramanujan gave for 1 over pi were discovered before he went to England. And they mention also that in 87, John and Peter Borwein succeeded in proving all the 17 Ramanujan series for 1 over pi. And in order to do so, the Borweins used, this is partially described in this survey, the Borweins are using relations such as this. It's a variant on our introductory example. We start again with the squared version of the theta 3. Instead of the lambda in the argument we have here, in this case, we find 4 times, so the k squared is lambda, 4 times lambda, 1 minus lambda. You see that the 1 over 2 changed to 1/4, 1/4. And this is one of several entries in the book by John and Peter Borwein. So they list, I think it's about 13 or 14 in a row, identities of this time. It's now 1 over 8. It's 1 over 12. This is in the Klein invariant the development. They use what they called Ramanujan's invariant. So Ramanujan's work was essential, and what I'm discussing here is the Borwein version of how Ramanujan came up with this approximation. Formulas, to my knowledge, we still don't know what he really did, but I can tell you what the Borweins did. Instead of doing so, this is another series of identities the Borwein came up with. It's the 3F2. You just square this. If you know Clausen's identity, you can go from previous identities to these identities. But with the approach I'm showing you now is you can do the following. You just fix this as the modular form. You multiply this modular function to the left-hand side, and you just produce these coefficients on a conjectural basis, and you prove this relation by proving the underlying differential equation. In a similar fashion, you can prove classic relations by Fricke and Klein. So for instance, here we look at the Eisenstein 4 series, we look at the Klein invariant J function, and we are studying the problem to relate. It's a modular form of weight 4. We relate this with the Hauptmodul. J is a Hauptmodul inverse because we start here 1 and we have Q development 1 over Q, so we have to invert. So we are interested in these coefficients. With the same method I described, you are led to conjecture a recurrence for the CK. Here it's not of order 1, it's of order 2. It doesn't look so complicated. It's already quite a complicated thing. Still, it's linear with polynomial coefficients. It's holonomic. And if you know that this is of weight 4, and if you know the theorem that was quoted by Ja Yee, then you expect, if you translate this into a differential equation, you expect a differential equation of order 5 here because of weight 4. So what you can try, and this is what Klein and Fricke did, you take the fourth root of the Eisenstein, then the weight reduces to 1, the differential equation goes to order 2, and then you expect that the corresponding recurrence is of order 1, and indeed you can check again with the mechanism I showed you that you get an order 1, you get the closed form for the coefficients involved, and you can with the same principle derive these classical relations. If you use Clausen's formula, you square the whole thing. You just have now the second root. You get something that is of interest to people studying Calabi-Yau varieties. But all these kind of formulas, here we don't need Clausen's formula. You just, with the tools I showed you, you conjecture the closed form of these coefficients. You conjecture the recurrence for the coefficients, you transfer it to the differential equation, and then you use the algorithm to prove the underlying differential equation. Beckers did an irrationality proof different to Apéry. He fixed this modular form. He used this modular function. You play the same game. You try to find coefficients that relate this modular form with this modular function, and you find for the coefficients, you find which recurrence, here's the question asked, which recurrence do these coefficients satisfy. You find this recurrence here at the bottom. Maybe, yes, I have here in the middle of the screen. This is the recurrence we find with the same principle. We can prove the full relation with, by proving the underlying differential equation. And as a remark, these numbers in this context are the famous Apéry numbers. Usually people, so in particular Apéry, use the sum representation of these numbers in order to prove that these numbers satisfy this recurrence. With this approach, or with Beckers' approach, you avoid the sum representation. Here you derive the validity of this recurrence by going to the corresponding differential equation. Let me conclude by showing you maybe one, on fly, a second example where we have not a differential equation, but an algebraic equation for the corresponding, in the corresponding setting. Now the G is a modular function. So for the G, for instance, we start with the generating function of two colored Frobenius partitions that were studied first by Andrews. We multiply in an eta quotient to make this member of a modular function family. We take another modular function, ideally with a small order. So there is no order 1 eta quotient, no order 1 modular function here. So we take the smallest one with order 2. Essentially, Atkin knew already how to do this. And we ask again, using this G and using as the H now the square root, as I showed you, if you have order 2, you want to expand and you have to take the square root in order to guarantee the existence of such an expansion. Here we start on the G side with -9. So we need to start here with -9 and we look at the corresponding coefficients by applying the same methodology, but now using the algebraic equation instead of the differential equation. We find a recurrence. This is quite involved for these coefficients, but the advantage here is in the algebraic relation. This algebraic relation, you might not agree, but it's really nice because you see there is 10, there is 25. This is divisible by 5. So we know that 5 divides the G. So the G squared. So we know that 5 divides the G. So this way, the proof is simple. The proof of algebraic relation, since this is modular functions only, is just verifying the first coefficients involved from -9 to 0. So back to what we observe from the algebraic equation, we find that this divisibility of 5 of the coefficients at 5n plus 3, we find this by just looking at the algebraic equation. And finally, I'm running out of time. Let me show you, let me connect again back to Ramanujan, who observed that these partition numbers are divisible by 11. We set up, we use as the G again, we multiply in this generating function of interest, an eta quotient to make the G member of a modular function family. We use an appropriate F. We take the F again, we need to do the square. We derive, let me first show you the algebraic relation between the F and the G. This is very compact. This algebraic relation can be proved by trivial verification. It's only modular function. First we guess it, then we prove it. And from this algebraic relation, you see that there is an 11 explicitly there, there's an 11 explicitly there. So 11 divides the G squared. So 11 divides the G. The G is this generating function. So the 11 has to divide each of the coefficients here. So we have an alternative proof, completely derived, completely computer assisted for the classic observation of Ramanujan. And with this tool, you can do all further things, but I think I need to stop here. Let me just repeat. This is what I presented you is a new algorithmic approach for proving and discovery of relations of this form, where the G is a modular form or a modular function, and the H is a modular function. And since I wrote in the abstract something on this line, so this the CKs, they all satisfy a model, let me say it again, the CK all satisfy a holonomic relation. This means a linear relation with polynomial coefficients. You find such sequences not so frequently in Ramanujan's work. What you find is you find such sequences in disguised, in hidden form, in context like this. This is another point I wanted to make because I think it's adequate. We are celebrating his work here. Thank you for attention.
Thank you very much, Peter, for a very nice talk. It's very nice to see how one can prove the classical as well as new relations from here. We will start with our second talk. So the second talk will be given by Professor Ja Yee from Pennsylvania State University. And she'll be talking on overpartition analogues of the generalized Rogers-Ramanujan identities of Bressoud.
Hi, thank you very much for the nice introduction, and it's my great honor and privilege to speak on Ramanujan's birthday. So thank you, Arthur, and the organizers for inviting me. So Ramanujan and his work has influenced many areas of mathematics, so it is impossible to discuss all his discoveries for 1 or 2 days. But today I'm going to talk about my recent work related to Rogers-Ramanujan identities. And this talk is based on joint work with my student, Shuriji Bandiopadhyay. Sorry for my bad pronunciation. And let's see. Okay, so this is Ramanujan's famous picture, the passport photo, which we saw already earlier in Bruce Barron's lecture today. So let me start out. by stating the Rogers-Ramanujan identities. When Ramanujan first discovered these identities, he had no proof, but he found the proof several years later. And a year after his proof, actually he found the work of Rogers on these identities. So now they are called the Rogers-Ramanujan identities. Before I proceed, oh, this is the picture of Rogers, L.J. Rogers. And before I proceed, let me define integer partitions. Although I believe most of us are familiar with it. So partition lambda is a sequence whose sum equals n, a partition of n. And here is an example of partitions of 4. So there are 5 partitions, and we denote the number of partitions by p of n. And the generating function of the partition function has this nice infinite product representation. Okay. And also I need some Q-series notation, the standard Q-series, Q-Parkheimer symbols, and some compressed notation, shorthand notation. Okay, then using those notations, we can actually write the Rogers-Ramanujan identities in this way. And when delta equals 0, it becomes the first Rogers-Ramanujan identity, and delta equal to 1, it becomes the second one. Okay, and the right-hand side, the infinite product has a nice combinatorial interpretation, which is the generating function for all partitions into parts congruent to when delta equals to 0, 1 plus minus 1 mod 5. Okay. On the other hand, the left-hand side, the summation has more than one actually combinatorial interpretations. Okay, and the well-known one is the first one, the conditions, part difference conditions. So it generates partitions with parts different by n least 2. Okay. Then when we have a nice infinite product like this, it is quite natural to ask if we can generalize it. Okay. And for the infinite product on the right-hand side, we can take, instead of 5, take a different modulus. On the other hand, for the summation, we can change the part difference condition from 2 to d. So possible generalization we can think of is the following: partitions with parts differing by n least d for d greater than 2. But unfortunately, there exists there is the orders non-existence theorem, okay, which shows there does not exist any set such that the number of partitions with parts differing by n least d equals the number of partitions into parts from the set. Okay. However, in 60s, Gordon actually considered the repetition of 2 consecutive numbers instead of the difference between 2 consecutive parts, and he found a nice generalization. Okay. So here is the Gordon's generalization. So A of n counts the number of partitions of n into parts, now congruent to 0 plus minus a mod 2k plus 1. And the bka of n counts the number of partitions of n such that parts of size 1 appears at most a minus 1 times, and lambda j minus lambda j plus k minus 1 differ by n is 2. In other words, we allow some repetitions. However, we may repeat same part or part 1 bigger than that, n most to actually k minus 1 times. So the second condition tells us that repetition restriction condition. Then Gordon showed these 2 partition functions that are equal, and about, let me see, yeah, a little bit. Yes, and then soon after, Andrews found this nice analytic identity that is equivalent to Golden's partition theorem generalization. So we call this Andrews-Golden generalization or Andrews-Golden generalized Rogers-Ramanujan identities. Okay, then actually looking at the right-hand side, Bressoud noticed that there is only odd moduli. So he looked for even moduli generalization, and he successfully found such one. So here A, Ka delta of n counts the number of partitions of n into parts not congruent to 0 plus minus A mod 2k plus delta. So actually when delta equal to 1, it returns the Andrews-Golden generalization. And when delta equal to 0, we get the even moduli generalization. And BKA delta of n counts the number of partitions of n such that it satisfies the following conditions. So here the first two conditions are the same as the earlier one, but he has this extra condition. Okay, so if the the two consecutive numbers, say I and then I plus 1 appears exactly k minus 1 times, then the maximum number of times, then their sum has to be congruent to A minus 1 mod 2 minus delta. So when delta equal to 0, mod 2. When delta equal to 1, actually this condition is always hold. Okay, so here is the note about the the Bressoud generalization. Actually, that generalization covers the Andrews and Golden. And here is he also found this nice analytic identity for his generalization. Okay. All right, then at the moment, let's switch our gear to overpartitions. Overpartition was introduced about 20 years ago by Cotil and then Lovejoy. Since then, many partition theorems were generalized to overpartitions. Okay, so here is a definition of an overpartition. There are mainly we can allow the overline of a part and its first occurrence. So for example, when n equal to 4, here part 4 may not be overlined, or we may put a bar to distinguish it from the partition 4. Okay, so there are altogether 14 overlined overpartitions of 4. So we denote the number of overpartitions of n by p bar of n, and the generating function of a p bar over n from the definition, you can easily see it has this nice infinite product representation. Okay, and to proceed further, I need for notational convenience, I need a frequency notation. So here f sub j denotes the number of non-overlined parts of size exactly j, and then fj bar counts the number of overlined parts of size j. And then we call this sequence the frequency sequence or multiplicity sequence of partition. Then the conditions for the Bressoud generalization can be rephrased as follows. Okay, so as I mentioned, many classical partition identities have been generalized to overpartitions, and Jeremy Lovejoy actually he considered generalization of Andrews-Golden's theorem, and then he found a nice generalization, which is the following. So he defined these two partition overpartition functions. So A bar counts the number of overpartitions of n in which non-overlined parts not congruent to 0 plus minus a mod 2k. So there is no restriction on the overlined parts. It has only the non-overlined parts restriction, and that reduces to actually the the Bressoud even moduli partition function. And B bar Ka of n counts the number of overpartitions of lambda with this with the frequency restrictions. So F1 is bounded by a minus 1, and then FL plus FL bar plus FL plus 1 bounded by K minus 1. So actually, if there is no overlined part, then this one reduces to the Andrews-Gordon partition function. So we can view this one as a overpartition generalization of Andrews-Gordon's theorem. And Lovejoy actually showed that these two overpartition functions are equal when A equal to 1 and then K. And several years later, actually 3 people from China, Chen, Sang, and then Xi, they confirmed that this holds true for any A between 1 and then K. So here is their result. And also they provided this nice analytic identity. Okay, all right. And then what about the Bressoud even moduli theorem? Is there any overpartition analog? And then yes, we do have. So here, because the infinite product generating function is more or less clear or obvious, so I'm going to focus on the gap condition. So B bar Ka 0 of n counts the number of overpartitions of n such that we have these restrictions. So the first one and then the first two are the same as before. But the Bressoud even in the mod 2 congruence condition in the Bressoud even moduli theorem is replaced by this third condition. So when the FL plus FL bar plus FL plus 1 equal to exactly K minus 1, then we have this similar mod 2 congruence condition. And actually, if we do not have any overlined parts, then this one reduces to Bressoud even moduli theorem. So then they show that actually this partition function, overpartition function B bar Ka 0 of n has this nice infinite product identity, product representation. Okay, so then what? This is not the end of actually the story. And while working on our project, Shuichi and I found another overpartition analog. So here, C bar Ka of n counts the number of overpartitions of n satisfying the following conditions. So here, as you see, there is no restriction on overlined parts. So it is much easier to handle. And then from the definition, we can easily see that the generating function for C bar equals the minus QQ sub infinity that accounts for the overlined parts. And then times actually the two conditions for C bar are exactly the same as the conditions for the Andrews-Gordon partition function. So times B bar B sub K minus 1 A of n. And from this, by comparing the infinite product generating function representation, we can easily see C bar equals B bar Ka 0 of n. However, nice thing about our work is, we actually found a nice combinatorial proof. And if I have enough time, then later my talk, I'm gonna show the combinatorial proof. Okay. And then about 10 years ago, Andrews actually investigated parity questions arising in partitions. And more specifically, he considered the following question. So WE counts the number of partitions enumerated by the Andrews-Gordon partitions with the following restrictions. Here, even parts appear only an even number of times. And similarly, we can define WO the restriction on the parity, even parts appear, replaced by the odd parts appear an even number of times. Okay, and then he found this nice Rogers-Ramanujan type, generalized Rogers-Ramanujan type identity. So WE has this infinite product representation, and then WO has this nice infinite product representation. And he couldn't find all the possible cases of K and then A, and the remaining cases were done by Khan-Carlson and Kim and myself. Okay, so then can we generalize this to apply this parity restriction to the overpartitions? Okay, so let's recall the conditions for B bar Ka of n. Then we have these two conditions, and then we can naively try to add this parity restriction. So even parts appears only an even number of times, but we don't get a nice identity. Instead, we had to modify the first two conditions a little bit. So here is W bar E, the overpartitions of n with these conditions. So F1 bounded by A minus 1 plus F1 bar. And we have these restrictions. And here is the parity restriction. And again, the gap condition restriction, okay, the repetition restriction. And similarly, we can define W bar O as well. Then a year ago, Sang Shi and then myself found this theorem. So the generating function for these two overpartitions. Okay. Then after this, I gave a seminar talk in my school, and then my student Shuris actually asked, "Can we do the same, game to the Bressoud overpartition analog?" So let's recall the condition for B bar Ka0. So here is the condition, the mod 2. And then again, we tried, our first try was to add just the parity restriction. However, unfortunately, we couldn't find a nice representation, generating function identities. But instead, we had to change it, modify these existing conditions a little bit, and then successfully found the Rogers-Ramanujan type identities. So here, the definition of these functions are very complicated, but bear with me. So U bar E counts the number of overpartitions of n with these conditions. So F1 bounded by this, and then the L bar is bounded by Fn. So if there is an overlined part L bar, then there must be at least one non-overlined part of size L. And we have this parity restriction, and then the repetition restriction. And moreover, because of the congruence mod 2 congruence restriction on the overpartition analog of Bressoud generalization, we have these restrictions, looking a little bit complicated. And then similarly, we can define U bar O as well by adding the parity restriction on the odd parts. And then Shuriti and myself found that there exists a nice generating function like this. Okay. All right, but surprisingly, we found another, while working on this, we found another analog, which is much simpler than the previous ones. So here, V bar E counts the overpartitions of n with these conditions. So there is no mod 2 congruence for the congruence like what we saw before U bar or the Bressoud generalization. Okay, so instead, And then we showed that this B bar E and then V bar O has, they have nice infinite product representation like this. And then by comparing the right-hand side, we can see this U and the U bar and the V bar, they are equal. Okay. All right. So I have about 5 minutes left. So for the rest of my talk, I'm going to briefly sketch the proofs of my theorem. So here, these are the theorems we got recently. And then the first theorem about the generating function for V bar E and then V bar O. The proof is based on the Q difference equations. And the later two theorems, the middle one, we can prove it combinatorially. And then the last one, we can also prove the generating function for this U bar using the Q difference method, Q difference equation method. However, the computation is really complicated. So I'm going to give a combinatorial proof showing that the U bar equals the V bar. Then as a bypass, we get the generating function for U bar E, which is the same as the right-hand side in the first theorem. Okay, so let me skip this. And then the key player in the first, in the proof of the first theorem is this infinite series. And then I'm gonna let the specialize this. So take a z to -1 over q, and then x by x to xq in this h tilde. Then we get this a little bit simpler infinite product. And I'm gonna call, infinite series. And then I'm gonna call this series q tilde kaxq. Okay. Then let's define z and then z tilde. I'm gonna focus on the even case because the even k and then even a case, because they are easier than the odd and then odd k and then the other cases. But we can easily actually prove the other k and then a case as well. So here z 2k 2a, I'm gonna set this thing the infinite product times q tilde, and then z tilde is this infinite product times q tilde ka. Okay, then with some simple Q series manipulation, we can show z and then z tilde satisfies this Q difference equations with these initial conditions, and then for V bar E and the V bar O, we need an the extra variable that keeps track of the number of the parts. So m comma n counts the exactly the overpartitions counted by this overpartition function V bar E with the exactly m parts. And then let's define a two variable generating function for such overpartitions, V bar E xq and the V bar O xq. Then again, using combinatorial argument, we can show that these two variable generating functions satisfy these recurrence relations. Q different, Q not a recurrence relation, Q functional equations. And actually, this functional equation matches the earlier one. So we see that V bar E is exactly z 2k 2axq, and by specializing letting x be 1, we get this infinite product, the minus q square infinite, and then q tilde, and then by here this x square has to be 1. And so when x equal to 1, this q tilde ka by the Jacobi triple product identity becomes this nice infinite product identity, the representation. So from this, we get V bar E and then VOE. Okay, and for the remaining two theorems, I do not have enough time, but the idea is we set up bijection between two overpartition sets, okay, so that actually there exists, they are equinumerous, and that shows, the two overpartition functions are equal, okay. And similarly, let me skip this. And similarly for the U bar E and the V bar E, we can modify our previous, earlier bijection to get the bijection between these two, and that bijection actually shows that they are equinumerous, and that completes our proof. So sorry at the end, I was a bit rushed, but this is all I have for today. And then thank you very much for your attention.
Thank you, Professor Yee, for a nice talk. So I was just curious about how you got to the terminology on troublesome or problematic.
So which one?
Yeah, the troublesome and problematic. Yeah. Okay, so.
Yeah, so those are the indices we don't want to see in our partitions generated by counted by actually in this case C or V. So we looked for some terminologies, and then we decided to go with it. It's a problematic. So yeah, that's all. Maybe you might have a better idea about these terminologies.
I was just curious to see. Yeah. Thanks very much for the nice talk.
Thank you.
Yeah. So next talk in this session is by Professor Frank Garvan from University of Florida, and he'll be talking on the unimodal sequence conjectures. So, Frank?
Hello, can you hear me?
Yes.
Okay, all right. Do I need to do anything to share my screen?
I think you'll have to click on the share screen green button at the below.
Ah, I see. All right. How's that?
Yeah, that's good. You can do full screen, I think.
Full screen, okay.
Yeah, perfect.
That is good?
Yes.
All right. So thank you, Atul, for inviting me to this special session for Ramanujan as part of the Special Functions Conference, and thanks to all the organizers. So the title of my talk is the Unimodal Sequence Conjectures. So the first thing I want to point out is that this is joint work with Rong Chen. So Rong Chen visited me for the past year at the University of Florida. He and his partner Dan Chen are from the University of Shanghai, and they are working on their PhD. And we did some fabulous research projects together. And because of COVID, they were stuck here longer than they wanted to, but I came up with a nice problem for them to work on, and this is the result. Okay, so anyway. So here's an overview of my talk. So I'm going to look at 3 sequences and 3 conjectures, ask some questions, make a connection with the Hurwitz class number, and of course, Ramanujan has to be involved somewhere, and he always is, well, almost always. So there's connections with the Ramanujan's Mach theta functions. Okay, so I'll basically skip that. So here's a picture of my co-author, Rong Chen. So Rong, if you're watching, I'm saying hello to you now. And I want to thank you again for your fabulous work in this project. And if it wasn't for Rong, this would not have happened. So this is a picture of Rong. We're working in my office at the university when things were normal. You can see my bicycle in the background there. So, all right, so these are the two sequences that there's three sequences. There's two sequences that start off with. There's this sequence U of n and V of n, and they're given by these generating functions. So this first guy here is the generating function for U. This is a generating function for V. And luckily, the previous two speakers have given me the notation. So here's the first conjecture. So suppose P is prime congruent to 7, 11, 13, or 17 mod 24. And suppose K is a quadratic non-residue mod P. Then we have this infinite family of congruences mod 4 for the coefficients of this function here. Okay. So here's a dramatic example. So the first prime to look at is P equals 7. I put K equals 3, S is 2. For dramatic effect, I pick N equals 20. And so there are this many things counted by U of 999. And as you see, this number is divisible by 4. Okay. I wouldn't want to count these things by hand. Okay. So these numbers grow pretty fast. Here's an asymptotic found by Rhodes in 2012. So it's like it looks like the asymptotic of the partition function, except this factor down the bottom is different. Okay. Now, remember, if I go back to slides, now we're looking at this sequence V of n, which is given by this generating function. So in 2016, Kim, Lim, and Lovejoy had this conjecture, similar conjecture. This time, P is not congruent to plus or minus 1 mod 8. They actually made a mistake in their conjecture, and they should also eliminate 1. But anyway, that's a small thing. So a similar conditions and similar type, so infinite family of congruences mod 4. Right, so one thing to ask is, what are these things counting, this U of n? Well, what you can do is you put the q to the n plus 1 in the middle, and you put these two factors on either side, and you basically see these are counting what's called strongly unimodal sequences. So this factor n plus 1 in the middle corresponds to the peak here, and the guys to the left are the sequence to the left, the guys to the right are the sequence to the right. So we're basically counting things that look like this. So U of n is the number of such sequences. Here's an example. There are 6 strongly unimodal sequences of the number 5. You can see here are the peaks. There's the biggest number here is 4, 3, 3, 3, 4, and 5. Okay, so that sort of tells you what's going on. Now, what's my third sequence? So the third sequence is the Andrews Spt function. So you're looking at all the partitions of n, and you just count the number of smallest parts. So here are the 5 partitions of 4. I've put a dot over the smallest parts, and if you count all those dots, you'll see there's 10 of them. So Spt of 4 is 10. So in 2008, Andrews discovered an amazing sequence of congruences for these guys. They look like the partition congruences, except they're for not only 5 and 7, but instead of 11, it's mod 13. This is truly amazing. And this has spurned a lot of research ever since, and don't want to get too distracted. Now I have a paper with George Andrews and Ja Yee in 2013, where we actually prove exactly when the Spt function is odd. So Spt function is odd exactly when this condition holds and P is a prime congruent. Well, of course, P has to be congruent to 23 mod 24, just looking at this thing here. But anyway, I better move on. So in 2017, I gave 2 talks at the AMS conference in Atlanta, which is unusual. So if you were at one of those talks, I made a conjecture for the Spt function mod 4. And this looks a lot like the conjectures for U and V by the Ono group and the Lovejoy group for U and V. Okay, so when I made this conjecture, the trouble is this conjecture holds for an infinite class of primes. So if it was just a finitely many primes, then we would know what to do. But with an infinite class, it's much more difficult, even though things may be connected with modular functions. So I had no idea how to do this congruence. And this is one of the problems I gave to my visitors from Shanghai, Dan, Chen, and Rong Chen. Okay, so we'll move along. So you can see at the top here, I said, have you seen congruences like this? Well, here's another congruence that you've seen like this. So what's on my next slide? My next slide is, have you seen modular examples? Well, before we tackled the SPT problem and the U and the V problem, we said, can this behavior happen for modular functions? So we found 3 examples. These are the generating functions for A, B, and C. So A of n is the number of representations of n as the sum of 2 pentagonal numbers and 3 times a triangular number. And B is C and simple as well. If you want to see them in a different way, this is a generating function for A, this is B, this is C, and you can write them as eta products. And I thank Peter for telling us what the eta function was in the 2 talks back. Okay. And in this paper that is actually online now in the Bulletin of the Australian Math Society, we have these 3 congruences mod 4, which are similar to the things for the U and the V and the SPT, but the generating functions for A, B, and C are modular forms. However, I wouldn't say that the proof of this was easy either, but the main ingredient was connecting this with the sum of 3 squares, and the sum of 3 squares is intimately connected with the class number of quadratic fields. So that was the clue. So I'm Australian, and we got this done in the Australian Journal. I have to feel sorry for the Indians watching the talk today with your, you know what happened with that cricket match, right? Anyway, I won't say any more about that, but I'll just say, I'm sorry. Okay, so what's the Hurwitz class number? So the Hurwitz class number is defined by these 3 conditions here. So basically it's when n is congruent to 0, 3 mod 4, and it's a class number of certain quadratic forms in 2 variables. And basically a quadratic form in 2 variables, 2 forms are equivalent if there's a change of variables, x goes to ax plus by and y goes to cx plus dy, where the matrix ABCD is basically in SL2Z. So if you count those equivalence classes, the number of equivalence classes is this class number, except we weight forms that are multiples of this guy by a half and forms that are multiples of that guy by a third. And there's the first table there. And you might wonder, what does it mean for this number here to be minus a 12? Okay. Kind of a mystery, right? All right. So this object is well known. It goes back to Hurwitz. And it's connected with, see, there's the H of D. This is the class number of the imaginary quadratic field. Omega is the number of units. And there's a more general formula when this is not a fundamental discriminant. It involves a Möbius function and the sum of divisors. So these things are well known to people who work in algebraic number theory and stuff. Okay, so here's some properties of the class number. And the important thing here is that n is congruent to 3 and is square free. So here it coincides with a class number, and there's a power of 2 that comes in that corresponds to the number of prime factors in n. And here's another formula that is related to the Kronecker symbol. And as you can see, this class number is odd if and only if n is a prime. Here we're assuming, of course, n is square free and congruent to 3 mod 4. But we want to know stuff mod 4. Well, back in 1970, Hasse proved that this number is 2 mod 4 if and only if n is a product of 2 primes, where this quadratic symbol is -1. It doesn't matter which one is on top or on the bottom because n is congruent to 3 mod 4. So at least one of these guys must be congruent to 1 mod 4. So when I turn it upside down, I get the same thing. Anyway. So remember, h of n is the Hurwitz class number. So this theorem here is Herzenbruch and Zagi in 1976. This is the first example of a harmonic massful of weight 3/2. This part here is a non-holomorphic function. The theta in the numerator here is the theta 3 function, the classical theta function. And that's why we need the h of 0 to be -1/24. Otherwise, this wouldn't transform correctly. Okay. Now, we want to get from n square free to n not square free, and this equation will help us. This was in a paper of Olgren, Brinkman, and Lovejoy, but it probably goes back before them. So you can prove this either using the Zagier result, or you can use the result to do with the class number in terms of the formula that we had before on the other page. Okay, anyway, I've got to move on. How are we doing? We're doing okay. So now here, this theorem here, remember here, n is not square free. So what do? We use the results when n is square free, and then we use the previous equation here to go from n square free to not square free. And when we're careful in doing that, we get the theorem on the next page. So it turns out this is odd if and only if n has this form. Now this should look familiar to you. This looks very much like the SPT when SPT is odd. It has a similar sort of condition. And we can also say when it's not odd, when it's 2 mod 4, it has to satisfy a condition like this. So when n is square free, it corresponds to Hasse's result. When n is not square free and congruent to 3 mod 4, it generalizes to this. You might wonder, why do I multiply by 3? Well, sometimes h has a denominator of 3, so you multiply by 3 to make it look like an integer, but you don't have to worry about that really. So move along. Oh, I almost forgot about Ramanujan, right? I only have a couple of pictures in my talk. My first main picture was my co-author, Rong Chen. My second picture is Ramanujan. So there's a connection with Ramanujan's Mach theta functions. So here's one of Ramanujan's second order Mach theta functions. Now, if you look at this guy here, this looks very similar to the V of n function. In fact, it's related to a V function of Kim, Lim, and Lovejoy. I won't go into what it is, but they have a second conjecture where they prove this, where they conjecture this congruence mod 4. So this is a congruence for the second order Mach theta function. Looks very similar to the previous conjectures, right? Okay. However, this time, this thing is not a modular function. It's not a modular form, but it is a Mach theta function. And as you know, the Mach theta functions are basically the holomorphic part of harmonic mass series. Okay, now we need a result of Humbert, which is, this is the generating function for the class number of 8n plus 7. So this was in Humbert's very large paper in 1907. J1 is just the Q infinity function here. This is also in a paper of Watson in 1935. So this stuff, what I'm talking about depends on three people. The three people are Ramanujan, second person is Hurwitz, and the third person is Humbert. And the strange coincidence was all these three guys died in 1920. So exactly 100 years ago. So they're all contemporaries. Here's some elementary congruences. This is just the theta 4 function. Of course, this is congruent to 1 mod 2. That's congruent to 1 mod 2. And when you square this, of course, that's congruent to 1 mod 4. Okay, so that's basically all we need. So we want to connect Ramanujan's mock theta function with the class number. Well, luckily, in Ramanujan's lost notebook, he has this series for the A function. Here's Humbert's result. And the nice thing is, if you change Q to minus Q, you'll get something that looks like on the right-hand side here, except over here, if n is even, this is divisible by 4. So we change n to n being odd. And when we do that, we get the next line. And it's not hard to see that these two things are congruent to each other mod 4, because if I move this guy over here, I've got the square of a theta function that's congruent to 1 mod 4. So these two guys are congruent to each other mod 4, and that gives you the lemma. So with the connection with the Hurwitz class number, that means we know exactly when the coefficients of the A function are odd. And we know exactly what they are when they're not odd and what it is mod 4. Okay, so to be 2 mod 4, it has to satisfy this condition. So I should point out, in a recent paper on the archive by Li Quan Wang, he looks at most of Ramanujan's mock theta functions and has theorems about the parity of those functions. In fact, this first result here is in his paper, but he doesn't look at things mod 4. Mod 4 is much harder than mod 2, basically because mod 2, there are only 2 residue classes. Okay, so here I complete the proof of Kim, Lim, and Lovejoy's second conjecture. So what do? We look at this arithmetic progression. We need to look at 8m minus 1, and we get this congruence. And because K is a quadratic residue, P must exactly divide 8m minus 1. And the result about Hurwitz forces this to be even. And then what do? We want to show that the value of this is 0 mod 4. So we want to do is we want to show that it's not congruent to 2 mod 4. So we suppose it is. And that forces some equations like this, where there must be 2 primes, P and Q. We already have the P here, exactly P to the 1. But this quadratic symbol has to be minus 1. But out of this, we see that PQ is congruent to minus 1 mod 8, which means that at least 1 is 1 mod 4, which means those quadratic symbols are the same. But when you look at the quadratic symbol of Q mod P, it's Q times a square, but that's congruent to K mod P. But we've already assumed that that's congruent, that's 1, and that's a contradiction. So that means that this assumption up here, 2 mod 4, is false, and we know it's even, so it must be 0 mod 4, and that's the end of the proof. Okay. So what were the ingredients of the proof? Involved the mock theta function, stuff from Ramanujan's lost notebook, the Hurwitz class number, plus the result of Humbert for the Hurwitz class number. I'm looking at my clock, and I'm still got a little bit of time left. So here's the other conjecture. This is for the V function. Now to get a hold of, to do this guy here, we need some Hecker-Rogers series. So what's a Hecker-Rogers series? So Hecker-Rogers series is basically a double series where you've got a quadratic form in the exponent of Q, but it's an indefinite form. So you need to sum over a cone in the integer lattice so that the exponent is not negative. Anyway. All right, so here's an example. This goes back to L.J. Rogers, 1894, very famous identity. Hecker made a uniform study of these things and discovered this independently and the connection with modular forms. This appears in the work of Cutts and Peterson on affine Lie algebras, and George Andrews has a nice proof of this identity using his constant term method. But we need some Hecker-Rogers series. So let me just say that the A function has this kind of Hecker-Rogers series due to Mortensen. It means that if you compare these two series, they're basically congruent mod 2. And the nice thing is the infinite products at the front are the same. So we get that for free. And then basically you take the difference and you can argue that that difference is even. And since the product is congruent to 1 mod 2, then you get this for free. This is true mod 4. And then you just basically look at this exponent here and say, well, what residue classes must this miss? And you go through the argument. I won't go through it in detail. And basically, the reason you don't want 1 or minus 1 mod 8 is you want 2 to be a quadratic non-residue mod p, which forces these two numbers to be divisible by p, which forces p squared to divide this number here, but we know that only the first power of p divides 8m plus 7. And that basically tells you that these exponents don't appear, and we get these two actually congruent mod 4 on this residue class. And then we use our result for NA to get the result for the Kim-Lim-Lovejoy conjecture. So I'm going to finish there 5 minutes early, just in case you have some questions. So there. So sorry, I went a bit faster at the beginning there, but
yeah. So, are there any questions? So fine.
Can I ask a question here?
Sure.
So does the proof of the congruences for U and V also use this class number idea? The counting the number of class numbers, the number of ideals.
They're all connected. They're all connected with the Hurwitz class number, and they're all involve Hecker-Rogers series and some connection with Ramanujan's Mach theta function.
But they're not related to counting the number of ideals in a cyclotomic ring of integers, right? Like in the proof of Kim, Lim, and Lovejoy, they use this fact that to find the congruence, one has to count the number of ideals in the cyclotomic ring of integers for the mod 2 congruence, of course. But I'm just saying.
Yeah, I'm not sure I know what you mean. So you're talking about this refinement with class function? Or?
No. So basically what they do is they actually count. So basically there's a binary quadratic form. Right. associated to the generating function. And then from the binary quadratic form, they consider a series which runs over those ideals inside the cyclotomic ring of integers. And they basically count the number of cyclotomic ring of integers. So basically the problem is converted to algebraic number theory, and they use results from there.
But what cyclotomic field are you talking about?
Like OK or something, the cyclotomic ring of integers. Like K is some specific ring of integers.
Okay, yeah, I'll have to look at that paper to find out exactly what you mean. But
so this U and V are.
I mean, there may be a connection. Yeah, I have a feeling there might be part of our paper where we do need something related to that, but I can't remember the details.
Thank you.
But anyway, thank you for your question. All right.
Any other quick question?
Professor Garvan?
Yes.
Yeah, I have seen your paper on archive. So I have seen that you studied the multiple behavior of 5 modular functions. So a natural question is, have you ever searched for similar congruences for other modular functions? I mean, just by computer or not for proof?
Yeah, I think we've looked at some other things and found some things, but yeah, nothing definite. I think Rong Chen and Den Chen may be looking at that as well. If they could answer that too. I'm not, but I got so many things to work on, and anyway. But it's a good question, though. I mean, it's a natural question. I think I make that question at the end of my paper. You know, you should look at other functions and see what you can do with those. But I mean, it would be interesting to see, could you go to mod 8, perhaps? I don't know. I mean, there are results for the class numbers for higher powers of 2 than 4, but things get more and more complicated as you go. So I'm going to sneak in a picture of my grandkids. And I better stop there because I know the next speaker will probably want to start soon.
Yes, thank you very much.
You're welcome.
And thanks, Frank. Thanks, Frank, for a very nice talk. So,
all right, thank you.
Yeah. So our next speaker is Ken Ono from University of Virginia, and he'll be talking on variants of Lehmer's conjecture on Ramanujan's tau function. Over to you, Ken.
Yeah, can you hear me?
Yes, we can.
I wasn't quite ready. Just give me a moment.
Sure.
Can you see my screen?
Not yet.
Oh, okay. Just one moment, please.
Sure.
Can you see my screen now? Maybe there's a small delay.
Yeah, we can.
Okay. All right. But now this is my screen. I'm sorry. Just give me 1 second to. All right. I have. There we go. Okay. All right. Let me get started then. Is that good?
Yes, it is.
All right, great. So I'm going to give a lecture on variants of Lehmer's conjecture for the tau function. And since time is limited, let me just get started. Let me say that I will be talking about 2 papers that are joint work with Jennifer Balakrishnan, my student Will Craig, and my postdoc Wei Lun Tsai. And I'm starting. So Ramanujan's tau function, happy birthday to Ramanujan as it is today, is defined many ways. The most concrete and lowbrow way to define the tau function is that these are the integers which form the sequence of coefficients of this infinite product, beginning with these famous numbers. It's a prototypical cusp form, the prototypical modular form. And what that means is, as a Fourier expansion, where Q is now replaced by the formal uniformizing variable at infinity, e to the 2 pi I z, it means that the function delta, which has tau as its coefficients, satisfies this transformation law with respect to all the Möbius transformations from SL2Z. Here Z is the variable representing the upper half of the complex plane. And as is well known, this function is ubiquitous. The delta function itself appears many places. Modular forms that have some of the same properties as delta appear many places. And since time is limited, let me just say it appears like everywhere, from combinatorics to number theory to arithmetic geometry, physics, and representation theory. This function is everywhere. Despite the fact that this function and its relatives are ubiquitous in mathematics, and despite the fact that many theorems are now known using a whole hodgepodge of very difficult techniques, from Galois representations to automorphic representations to the theory of L functions, despite all of that work, which makes use of the fact that the coefficients of tau are much more than just the coefficients of a power series. It turns out that a very simple to state problem remains open. Lehmer's conjecture that tau of n is never zero, which he really made more of as a speculation, but we refer to it as Lehmer's conjecture, remains open. Very little is actually known about it. What is known, when Lehmer speculated this, he himself understood that he could use the multiplicative power properties of tau together with the elementary bounds on tau to show that if tau ever vanished, there would have to be a prime p for which tau of p vanishes. So Lehmer's conjecture is equivalent to establishing the non-vanishing of tau at primes. What is known? We don't know that tau of p can never be zero, but using an infinite direct product of Galois representations, Serre in the early 1980s, making use of the very deep theory of Deligne, was able to prove that if tau of p ever vanishes, the set of primes p for which it vanishes must have density zero. It's very thin. There have probably been 2 or 3 dozen papers building on this famous Chebotarev density argument of Serre. And the current world record, I think, is due to Jesse Thorner and Asif Zaman, where the world record gives you an upper bound on how small density zero is out of the primes up to x. Now, the variant that I want to discuss is the following. There really is truly nothing special about zero. It's the first number you would consider trying to study with respect to multiplicative functions. But apart from that, there is no real special reason why we want to study whether or not tau is zero. And so the question I want to ask, and many people, it's not that I asked, rather that has been asked many times, is can tau of n equal an arbitrary integer alpha? And the first theorem that I'm aware of is a beautiful theorem by Murty, and Shorey in the late 1980s. And they proved that for odd integers alpha, there are most finitely many n for which tau of n equals alpha. Their proof makes use of the theory of linear forms and logarithms, which is quite prohibitive computationally. And so before the works I'm describing today, the only odd integers alpha for which the question, can tau of n equal alpha? The only alphas for which that has been solved before this year were alpha equals plus or minus 1. So this is what is typical in the theory of linear forms and logarithms. There are statements that say things along the lines, there is an effectively computable constant such that if tau of n ever equals alpha, then n is less than e to the something to the something to the something to the constant. And computing this constant is very difficult, still has not been done. So I want to tell you about how you can prove this theorem again without actually needing any of that stuff. And I'd like to show you how you can prove it in an effective way so that we can actually answer this question for many specific choices of alpha. And without running too much computer code, let me offer you this sample theorem. So this is in the work that I've mentioned with my collaborators, as well as the REU we had at the University of Virginia this past summer. And here's a theorem. If n is greater than 1, right, tau of 1 is 1. But if n is greater than 1, it is impossible for tau of n to be plus or minus 1 or plus or minus 691. And it's impossible for it to be plus or minus an odd prime up to 100. And there's nothing very special about primes. If alpha is odd, we have a general theorem that gives you a finite condition that you can check to decide whether tau of n is ever equal to alpha, an odd alpha in absolute value. So these theorems are very different from what you get from the theory of linear forms and logarithms. So I'd like to explain the idea and in the special case of alpha being primes in absolute value, explain how that works. Our theorems are actually much more general than just tau. So it's this setting. Suppose you have an even weight new form with integer coefficients. The integrality is important. If you have an even weight new form with integer coefficients with a residually reducible mod 2 Galois representation, then our theorems will apply. If you're not familiar what it means to say that a Galois representation is residually reducible, let me just get away from that. Let me just say what this condition essentially means in practice. Essentially, it means in practice that the AF of n's will be odd if and only if n is either an odd square or supported on finitely many square classes, the sort of things that you saw in Frank Garvan's talk a moment ago. And in fact, it's well known that Mach theta functions have mod 2 residually reducible Galois representations, provided you have the right ramification conditions. If you're familiar with the theory of elliptic curves, you probably know that all elliptic curves over Q are modular, and you know that modular elliptic curves have weight 2 cusp forms associated to them. If your elliptic curve has a rational 2 torsion point, then the modular form that you're studying automatically satisfies the hypothesis of the theorem I'm about to show you. So what is the general theorem? The general theorem is this. In the theorem I described a moment ago about the primes up to 100 is a corollary. It's a result of a calculation. The main theorem is this. Suppose you have an even weight new form that's at least 4. Weight 2 is a different matter, but we have theorems there. And suppose that the second coefficient is even. Then, if you have any coefficients that are a power of an odd prime, so L is a fixed odd prime, if any of the coefficients of your new form are a power of an odd prime, then we can locate that exponent. We can locate the position of that coefficient. So if AF of n is plus or minus L to the m, then n is greatly restricted. N has no choice but itself to be a prime power. By multiplicativity, that might sound strange, but this is a law. If AF of n is a prime power, then n is a prime power. But even better than that, not only is n just a prime power, the exponent in that prime power is greatly constrained. N is p to the d minus 1, where d is a divisor of L times L squared minus 1. There's no other way that a coefficient of a new form could be L to the m in absolute value unless it occurs precisely at ends of this form. So let me just give you an example. If L is 5, suppose you want to know whether a power of 5 is a Fourier coefficient of such a form. You first look for the d's. The only odd primes dividing 5 times 24 are 3 and 5. The only odd primes d dividing 5 times 24 are 3 and 5. So if a power of 5, any arbitrary power of 5 is a coefficient of your form, you only have to study a of p squared, that's where d is 3, or a of p to the 4th, where d is 4. A power of 5 can never be a Fourier coefficient of delta or any of the modular forms I'm describing, except at those special locations. So what's great about that is you can now very quickly and rapidly rule out numbers as coefficients of large infinite families of modular forms. So suppose you have any new form that I've described whose weight minus 1 is divisible by either 3 or 5. So for example, weight 16. Weight 16, 16 minus 1 is 15. 16 is at least 12. You cannot find a new form anywhere in mathematics where, apart from the first coefficient, you get plus or minus 1 again, or you get plus or minus an odd prime up to 37, but not including 37. At 37, you can rule out negative 37 as a coefficient, but you cannot rule out 37. How does that work? Well, it turns out our theorem does better than that. It actually locates the expressions. So in this last theorem, I indicated that I couldn't rule out 37. I couldn't rule out 37, although I can rule out minus 37. And why is it? Because in mathematics, there are plenty of weight 16 new forms whose 9th coefficient is exactly 37. But better than that, the only time 37 could ever be a coefficient of such of these forms is at the 9th coefficient. And that's a very powerful statement. So if you want to locate 37 as a coefficient, my theorem will tell you, just check the 9th one. If the 9th one isn't 37, you don't ever have to look again. So in particular, if you apply these theorems to E4 times delta, you don't even have to check anything at all. You already know that all the odd primes up to 100 cannot appear as the coefficients going off to infinity. What about the primality? So I'll sketch the proof there. If you haven't seen me talk about this before, that this probably sounds like very different kinds of theorems. So I'll sketch the idea. We also have theorems about whether or not tau can ever be prime. And it can. Lehmer himself in the 1965 found that tau of 251 squared is this giant number, which is prime. So you could ask, are there any other primes? And you could also ask, well, 251 squared is a rather strange place for a prime to occur. So you could ask for theorems about how many prime divisors tau of n has. Now, because the tau function is multiplicative, and because tau of n cannot be plus or minus 1 in absolute value without n equaling 1, it's trivial to show that the number of prime divisors of tau of n at least is as large as the number of prime divisors of n. But often it's much larger. So are there general lower bounds for the number of prime divisors of tau of n, including multiplicity, that go well above what one gets for free from multiplicativity? And we get such a theorem. So if n is a positive integer, not 1, then the total number of prime divisors of tau of n is at least as large as this sum. What is this sum? For every prime dividing n, you compute the power of p dividing n, add 1 to it, and compute the number of divisors of that strange number, one more than the exponent on p, for every prime divisor of n. You take away 1 from each of those tallies, add them up, and the total number of prime divisors of n, tau of n, is at least this. And it's easy to see that that's at least as large as omega of n, and it's generally larger than n, than omega of n, but not always so, of course. So how are these theorems proven? These theorems are proven by trying to avoid the theory of linear forms and logarithms in a smart way. And it turns out that there's some beautiful theorems of Urey, Ballou, and others, which when combined with the theory of Galois representations, and which when combined with the standard theory of modular forms, all together packaged together to give the theorems I'm describing. So first, the elementary number theory. So if I were given an integer sequence a of n, a of 1, a of 2 going off to infinity, we will say that an nth term has a primitive prime divisor if there's a prime L that divides the nth term, but does not divide any of the previous terms. So a term in a sequence has a primitive prime divisor if it divides a term in that sequence, but doesn't divide any previous term. Otherwise, we will say that a term in a sequence is defective. A term in a sequence is defective if all of its prime divisors occurred as a factor in one of the earlier terms. To give an indication of what that means, here is the Fibonacci sequence, and there's a beautiful theorem of Carmichael going back to 1913 that classified the defective terms in the Lucas sequence. I'm sorry, in the Fibonacci sequence. If this is the Fibonacci sequence, I've underlined and I've presented and read to you the terms which are defective, right? 144 is divisible only by 2 and 3. 2 and 3 occur as prime divisors of previous Fibonacci numbers. In fact, they are themselves previous Fibonacci numbers. But Carmichael's theorem is that 144 is the last defective term in the sequence. After 144, every term in the sequence is divisible by a prime you have not yet encountered in the Fibonacci sequence. And when I learned that theorem, I understood immediately that you could combine this with the theory of L functions to prove theorems of the type I'm describing. So the setting that we want to consider are the Lucas sequences. So suppose alpha and beta are quadratic algebraic. So, yes. And so by that, I want alpha plus beta their trace and alpha times beta their norm to be relatively prime non-zero integers. And I also want to assume that alpha over beta is not a root of unity. Then the Lucas numbers are the elementary sequence generated in this way. So for each in these alpha and beta, un of alpha beta is the hello? Okay, so the Lucas numbers are these integers. And the important thing about these integers is that they satisfy a two-term linear occurrence relation, which includes those which arise in the theory of modular forms. The great theorem about Bilou, Henro, and Voutier is that every Lucas sequence has the property that the last defective term, if there are any, occurs at latest as the 30th term. And so it turns out that with their beautiful classification, you can find all the defective Lucas numbers that exist among all Lucas sequences, all of them, not just a Fibonacci sequence. It turns out that this classification breaks into two categories: some sporadic examples, which are very rare, and they basically never arise in the theory of modular forms, except in the case of weight 1. In a few cases, weight 4, but basically they don't arise. And then there are the parameterized infinite families of these Lucas sequences, where there are primitive defective terms in the sequence. Of course, never after the 30th one. But what's great about this parameterization is it comes from geometry, meaning that you can classify all the defective terms using the arithmetic of hyperelliptic curves. And in many of these hyperelliptic curves, we can prove a priori that they don't arise in connection with the theory of modular forms. So the key lemmas about generic Lucas sequences that we require is as follows. If you have a Lucas sequence given by numbers alpha and beta, if D divides N, the dth Lucas number divides the nth Lucas number. Moreover, if L is prime, the first and if L divides some term in the Lucas sequence, then it turns out the first occurrence, if ML is the first N for which L divides the nth term in the sequence, can be computed. Rather than giving you the complete classification, let me just tell you, if L is an odd prime that doesn't divide the norm alpha beta, then the first time L divides a term in your sequence is a divisor of L times L squared minus 1. This is like an undergraduate number theory exercise. So if you combine that with the theory of new forms and the theory of Galois representations, you get the theory I described. What do we need? The fundamental features about new forms that generalizes what Ramanujan conjectured in his famous paper on the tau function is that all new forms have multiplicative coefficients, and on prime powers, the coefficients satisfy a two-term recurrence relation. The way I've decided to write that two-term recurrence relation might be a little bit different from what you're accustomed to, but it's very easy. If P is a prime of good reduction, the coefficient at P to the M is a Lucas sequence, is the M plus first term in a Lucas sequence given by this characteristic polynomial. So what is the strategy for proving a Lehmer variance? Well, it's now easy to describe. Let me only describe the case where we want to determine whether a prime in absolute value is a coefficient. It's very easy to generalize to arbitrary odds. So suppose that L occurs in absolute value as a Fourier coefficient. By multiplicativity and the fact that we've already established that AF of 1 cannot be 1 without N being 1, we find that N itself has to be a prime power. But by the theory of Galois representations, or in the case of the delta function using Jacobi triple product, that forces N to be an even power, right? So along the lines of what Frank was talking about a moment ago, the theory of modular forms and mock modular forms is chock full of Q series, which when reduced mod 2 look like theta functions. And that's all I'm saying here. Therefore, to study whether or not L occurs as a Fourier coefficient boils down to the problem of deciding whether there are any primes P and any exponents 2m for which AF of P to the 2m is L. But I want you to note that this is a Lucas sequence given two algebraic quadratic conjugates. We can rule out the defective Lucas numbers. I don't want to go into the details, but I assure you we can do that. All the theorems we've used make it very easy. In the case of delta, there are never any defective Lucas numbers. Therefore, by those two lemmas I showed you a moment ago, namely the lemma about relative divisibility as well as first divisibility, I can locate the 2m. Because every term in the Lucas sequence accumulates prime divisors, the only way L can occur as a L can occur, or a power of L can occur as a Fourier coefficient, is if it occurs the first time L divides the Lucas sequence, right? That's the great thing. Therefore, by combining these two lemmas, this 2m plus 1 has to be D, where D is an odd prime dividing L times L squared minus 1. That's our strong constraint. Therefore, the question becomes, how do we find all the primes P for which AF of P to the D minus 1 is allowed to equal plus or minus L? If you look very carefully, this is the stuff of algebraic geometry. This is the fact that on prime powers, the Fourier coefficients are required to correspond to integer points on algebraic curves defined over the integers with large genus. What does that mean? So if you want to decide whether AF of P squared is ever equal to an alpha, that can happen if and only if P comma A of P is an integer point on this elliptic or hyperelliptic curve. This is easy exercise. If A of P squared is ever equal to an alpha, you can detect it by finding the integer points with on this hyperelliptic curve. For A of P to the fourth, if A of P to the fourth ever equals a number alpha, then x comma y, being these two numbers, are an integer point on this hyperelliptic curve. So if you want to decide whether A of P squared of A of P to the fourth is ever a power of 5, where alpha is 5, all you have to do is establish whether or not there are any integer points on these curves where the x-coordinate is a prime number. Although that is not easy, we have the technology to do that. What about determining Fourier coefficients for higher even powers, not just P squared and P to the fourth? Well, this is easy to do. Write down a power series in T whose coefficients are functions in X and Y as follows. So if you expand this as a power series in T, the coefficient of T to the M is a function in X and Y. For even exponents, f of 2m, when you study T to even powers, this is actually a homogeneous polynomial in X and Y. If the exponent is odd, you've got square roots of Y flying around. But in the special case where the exponent is even, then it's very easy to show that the coefficient is given by this modified cyclotomic polynomial. When you let x equals 1, this is essentially the minimal polynomial for the maximal real subfield of the 2m plus first cyclotomic field. And let me just say, if you don't know how this works, it's not very hard. It comes from the theory of L functions by studying the local factor at P. If the Fourier coefficient of A of P to the 2m is equal to an alpha, it happens if and only if f of x comma y, where x is P to the 2k minus 1 and y is the square of the coefficient, is alpha. This is a rapid way of listing all the Fourier coefficient at prime powers for any modular form. What is the point? In this case, this defines a genus, positive genus curve. In the previous cases here, once the weight is at least 4, these are also positive genus curves. And the famous theorem of Siegel says that every curve defined over Z with positive genus has at most finitely many integer points. And there you have it. That's the simple proof of the Murty-Shori theorem. It's just a corollary of Siegel's theorem. Unfortunately, Siegel's theorem is famously ineffective, right? So the question is, how do you prove theorems effectively? This is where you have to bring into play some arithmetic geometry. We do that in the case of tau. That's how we arrived at this theorem. And just to sketch the proof, here were the first few steps as I described before. If you want to see whether an odd prime L in absolute value is a coefficient, find the odd primes that divide D times L squared minus 1. Write down, rule out, we need to rule out tau of P to the D minus 1 equaling plus or minus L. But as I've just explained, that becomes a question in arithmetic geometry. So you're either solving for rational points on elliptic or hyperelliptic curves, or you're solving what is called a two-way equation. That would take a bit of time to explain how that's done, but we have the technology to do that. And the technology includes theorems from Galois representations, computing what's called the Mordell-Weil group of the Jacobian of a modular curve. There are other methods using p-adic integration due to Chabot and Coleman. And if you combine all of that together, you can show that the theorems of the type that I've described. What is interesting is when you are unable to rule out a number as a Fourier coefficient, we've discovered without exception so far, it's because the integer point on one of these curves actually literally points to a modular form that you can find, for example, in the modular forms database. So what I like about this method, unlike the work on linear forms and logarithms, is that it proves the same theorem, that odd integers are only finitely often, if ever, coefficients of these modular forms. And it gives rise to geometric realizations of these points. And when the geometry says those points aren't there, your theorem is proven. Okay, so to conclude, here are a summary of our theorems. In the case of tau, you can check very easily on a computer that tau can never be these odd numbers. If you're interested in lower bounds for the number of prime divisors of a Fourier coefficient like tau, including multiplicity, we have a sharp lower bound here. And I think that's all I have to say about that. Thank you.
Thank you, Ken. Thanks for a very nice talk. Are there any questions? Yeah, Rajendra, you have a question?
Yes, sir. Good evening. Good evening, sir. Good evening, Professor Atul. Good evening, Professor Ken.
Good evening. Good morning for me. Yeah,
yes, yeah, you have morning there. Correct. Professor, I just wanted to have one thing. First of all, I'm a learner of number theory. I'm not expert of number theory. First of all, at my PG level, instead of higher arithmetic, I mean number theory, I had graph theory as a subject. So number theory is my, you can say self-learning course type of. So I don't know whether my way of posing the question will be perfect or not. I just wanted to know one thing, what we have to study for knowing this one.
Yes.
Universal form. Hopefully I'm audible. Yes. I'm talking about binary. Yeah, binary form I'm talking about, Professor Ken. Binary form, universal form, I just wanted to know, like pertaining to quadratic form. I just wanted to know what to learn and how to study those things, which things are to be prepared.
Well, so it depends, because the ring of definition of your forms plays a very significant role in terms of how you study things. So if you study, what you have to study start with Gauss. A modern treatment of Gauss's work on class numbers, which appeared, for example, in Frank's last talk, is a must. So there's a book by David Cox called Primes of the Form x squared plus ny squared. You could read it very quickly. There aren't many complete proofs, but the proofs that are there are meant to bring you up to a high level rapidly. After that, then you probably want to take a course in algebraic geometry, at least a first course, because so much of modern number theory, from this Q series to modular forms, even to applications in cryptography, really relies heavily on the ability to bring in tools from these different areas. So I would start with maybe primes of the form x squared plus ny squared, and then maybe a book by Sayre, A Course in Arithmetic, and maybe Koblitz's book. And at that point, you'll probably be ready for a graduate program.
Yeah. Thank you, Professor. Thanks a lot. Sure. Thanks a lot. Sure. And one more very small question. I mean, I don't know whether it is pertaining to the talk of the day or not, but what to study to understand the Andrew Weil's version of FLT for March last year?
Well, a lot of the things I talk about rely on those ideas. So after you read Koblitz, you can read this book by Cornell and Silverman. It's called actually Arithmetic Geometry. Almost every beginning graduate student who chooses to work in this direction should probably read that. It's called Arithmetic Geometry by Cornell and Silverman. There's a book by Lorenzini called An Invitation to Arithmetic Geometry, which is also good. But there are many expository arguments, articles on this. By the way, a lot of that is being rewritten. If you want to understand truly why elliptic curves are modular, It used to be up to about 3 or 4 years ago, you had to first learn a lot of Galois cohomology to see how that works. That's no longer true. It used to be, for the longest time, you first learn about elliptic curves immediately after you study what are called elliptic functions. Are you familiar with the Weierstrass P function and its connection to the Eisenstein series?
Yes, yeah.
Yeah, okay. So you can skip 50 years of work if you read the work of Eichler and Selberg.
Yes.
And the work of Eichler and Selberg and Shimura explain how you can construct an elliptic curve from a modular form. It makes use of what's called the Eichler Integral. And it turns out that if you substitute the Eichler Integral in the right way into the Weierstrass zeta function and apply what's called a theta lift, you get the weight 2 modular form of Wiles. It's a much more direct way to see modularity. It has its origins instantly in the theory of elliptic functions. And I don't know if anyone has written a book about that, but they're beginning to see some papers. And because of that, hypergeometric functions are playing a very central role in this. I mean, Wiles took everyone by surprise when he proved his theorem. So it takes time for everyone to catch up and know how to think about coming from elliptic functions and hypergeometric series, what he was talking about, and I think people are getting there.
Thanks a lot, Professor. Thanks a lot. Sometimes I might write for you, so please, without yeah. Okay. Sometimes I might write for you for material or something, like if you could.
Okay, I'm sorry. I don't always answer. I get like 300 emails a day, honestly. So
yeah, no problem. But whenever there will be this thing, not every day or something, whenever it will be possible. Thank you very much. Thanks a lot. Thank you very much.
Thanks very much, Ken, for a very nice talk.
Thank you, Professor Atul as well. Bye.
All right. The only other comment I want to make about this, or the content of the talk, is if you're wondering what role alpha being odd plays in this, in principle, almost nothing. This argument will apply almost mutatis mutandis for any non-zero alpha. So that's what some of us are working on in our research group now. And if we are lucky, I'd like to someday in the future report to you that we have the technology to test whether any non-zero integer is a coefficient along the lines of odds.
Yeah, that would be great. Yeah. So I remember at University of Florida, there was a conference in 2008 where you presented one more criterion for Lehmer's conjecture. I think it was in terms of certain integral, if I remember correctly.
Yes, that's correct. But you know, I never succeeded in finishing that program, because if you apply the method of continued fractions to those period integrals, you'd have to be able to distinguish integrality. You have to distinguish between algebraicity versus transcendence, and that's just so difficult.
Oh, okay.
Right. So I'm not trying to get a different criterion on Lehmer's conjecture. I'm telling you right now, I have no idea how to do that. The point is, in Siegel's theorem, at the end of the day, we want to bring all these ideas together to say if tau of n equals a number alpha, it's because n and alpha correspond to integer points on one of finitely many algebraic curves. And as long as all of those algebraic curves have positive genus, there can at most be finitely many n. And if those curves are sufficiently well positioned or formulated, we might have the technology to rule them out. That's my philosophy. But if alpha is 0, those are all singular curves. And when you do the typical Hironaka thing and do blowups to get a desingularization, all bets are off. We don't know how to do 0. 0, I don't think anyone will solve in my lifetime. It's just, it would take a completely different idea.
Okay.
Yeah.
Okay, thanks very much for the insight.
Thank you for listening, everyone.
Good. Yeah. So our last talk in this session is by Professor Rupam Barman from IIT Guwahati, and he'll be talking on Mex-related partition functions of Andrews and Newman. Rupam?
Yeah. So can you hear me?
Yes.
Okay, so I just share my screen. So can you see my slides?
Yes.
Okay, thank you. Thank you, Atul.
Yes.
And I thank the organizers for your kind invitation. So today I will speak on Mex-related partition functions of Andrews and Newman, and this is a joint work with my student Ojit Singh, and whatever we are going to present already available in the archive. And very recently, Andrews and Newman introduced partition functions coming from this Mex function. So I will just talk about this. Okay, so you know what is a partition? So partition is of a positive integer n is any non-increasing sequence of positive integers whose sum is n, and then the integers, positive integers in the partition are called the parts. And number of partition will denote by Pn. Okay, so for a set S of positive integers, the minimal excludant function, which Andrews called max function, is defined as follows. So max of S for a set of positive integers is nothing but the least positive integer not present in S. And then this Andrews and Newman very recently in early 2020, they generalized this function to integer partition. So how they define this function for integer partition? So what they did basically for a given partition lambda of n, they define the max partition. So they fix some capital A and small a, they are integers. So once you fix these two integers, and then they define this max function for every partition lambda of n to be the smallest positive integer congruent to a modulo n, that is not a part of lambda. So basically you are excluding the parts of lambda and taking the value which is congruent to a modulo a. Okay, so after defining this max function for the partition function, so they define the max related partition function p capital A comma small a and to be the number of partitions lambda of n which satisfy this condition. So this number max lambda is congruent to a modulo 2a. For example, let me explain this function with some example. Okay, so just consider this n to be 5, capital A to be 2, and small a to be 2. And then this max 2 comma 2 lambda is the smallest positive integer congruent to 2 modulo 2, and that is not part of the partition lambda. Okay, so if you now find this function for every partition of 5, okay, so for the 5, what we have that the 5 is the only part, and so you can take so I mean you have to consider this smallest positive integer to be 2, and that will be congruent to 2 mod 2. Similarly, for this partition, 2 is not a part of this partition, so again this max will be 2. Okay, so whenever 2 is a part, then the next smallest positive integer congruent to 2 modulo 2 will be certainly 4. So these values will be basically we are getting 2 and 4. Okay, and then we will see from here that 4 partitions of 5 satisfy this condition, that the max 2 comma 2 lambda is congruent to 2 modulo 4. Okay, so therefore this partition function takes value 4 when n equal to 5. Okay, so p 2 comma 2 of 5 is 4. So this is where basically they define this max related partition function. So they also gave the generating function. They established the generating function for p t comma t, and they proved that this is the generating function for this partition function, where this a comma q, this is nothing but the this infinite q product. Okay, and not only for p t comma t, they also proved the generating function for p twice t comma t. Okay, and then what they did after proving finding the generating function, Andrews and Newman studied the partitions p 1,1 and p 3,3 more closely, and they established remarkable connections between these two functions and the enumeration of partitions according to their rank and their crank. Okay, so let me just recall what we mean by rank. Rank is nothing but the largest part minus the number of parts. This is called the rank of a given partition. And then let me just define quickly what is a crank of a given partition lambda. So for crank, what we consider for given partition lambda, if L lambda denotes the largest part of lambda and omega lambda denotes the number of ones in that partition lambda, and mu lambda denotes the number of parts of lambda larger than omega lambda, then we define the crank of this partition lambda to be L lambda if omega lambda is 0, and if omega lambda is greater than 0, then it is defined to be mu lambda minus omega lambda. So in that paper, after introducing this Mex-related partition function, Andrews and Newman basically proved that this P1, 1n is nothing but the number of partitions of n with non-negative crank. And they also proved that that this P3, 3n equals the number of partitions of n with a rank greater than or equal to -1. So this is the mostly the work of Andrews and Newman in that paper. So after that, immediately after publication of this work, I think Da Silva and Sellers, they studied these two functions. Basically, they considered this parity consideration. So they studied the parity of these two functions, P1, 1 and P3, 3n. So they completely gave the parity of these two functions. They proved that this P1, 1n is odd if n takes this form, and it is 0 or is even. P1, 1 is even otherwise. They also proved that this P3, 3n is odd if 3n plus 1 is a square, otherwise it is even. And all these things are proved using elementary Q-series manipulations and the generating functions. So now I'll just talk about what we have done regarding this Mex-related partition function with my student Ujit Singh. So what basically we observed that this, although this Mex-related partition function is defined from a completely different point of view using the Mex function, but what we observed that this function satisfies the Ramanujan type congruences. So for the first thing, we established that it has connection to ordinary partition function. So how it is related that this Pt, T and is nothing but this can be expressed like this, where this Pn is the ordinary partition function. And here we consider the convention that adopt the convention that this Pn is 0 whenever n is a negative integer. So whatever we have, this series on the right hand side, that is eventually a finite sum. Similarly, we have expressed this P2 twice T, T in terms of these values of ordinary partition function. So of course, I mean, again, here the proof is not difficult. It comes from the these Q series manipulations of the generating function. And then from here, what we can prove, we also prove that these that these two functions satisfy Ramanujan type congruences. For example, what we proved that for positive integers m and a, and b is an integer, and suppose that the ordinary partition is 0 at a n plus b for all modulo m for all non-negative integer m. So suppose we have a congruence satisfied by the ordinary partition like this, then what happens that this Mex-related partition function P at, at and P2 at, also satisfy the same type of congruences, and this is for all non-negative integer m. Okay, so from here, what we can prove that that these two Mex-related partition functions, or these two families of Mex-related partition functions, satisfy all the Ramanujan type congruences. So we can easily have this result where these two families of partitions Pt, T and P3, 2, T satisfy these Ramanujan type congruences for certain values of T. So here, I mean, just you only thing you have to observe that this for what values of A and B you have Ramanujan congruences, and then for those values of A and B you have basically Ramanujan type congruences for these two families of Mex-related partition function. So the proof are, I mean, very elementary and uses only these manipulations of Q series and the generating function. Okay, so next we consider the parity of Mex-related partition functions. Okay, for some other families, So already we know that this parity is completely understood for t equal to 1 and t equal to 3. So p1, 1 and p3, 3 are completely understood by the work of the Selva and Sellers. Okay. So now what we consider, we study the parity for these two families of Mex-related partition functions, and we observe that parities of these two families are completely different from what from that of p1, 1 and p3, 3. What we prove that this is for t equal to 2 power alpha for any alpha greater than or equal to 1. So this is almost always even. So it is almost always even, and what basically that means that this set of positive integers such that these values are even. This set has arithmetic density 1. So in other words, this limit is 1. Okay, so this is completely different from what Selva and these Sellers obtained when alpha equal to 0, basically is 1, 1. But for alpha greater than or equal to 1, we have a completely different parity for this family of Mex-related partition functions. We also proved that for this family, 3 times 2 power alpha, 3 times 2 power alpha, this is also almost always even for all alpha greater than or equal to 1. Okay, that means this set has arithmetic density 1, or this limit is 1. Okay, so so then once we have this arithmetic density to be 1 is equal to 1, then of course necessarily what you can ask that example of congruences, because we have already know that this is almost always even. So we expect that there are infinite families of congruences modulo 2 satisfied by these two families of Mex-related partition functions. And exactly that is true, and we could actually find example of such infinite families modulo 2 for these two families of these Mex-related partition functions. And interestingly, what happened that the modular forms will be dealing with these two families of these two families of Mex-related partition functions. The level for that modular form lies in the list given by Ono and Taguchi regarding the nilpotency of Hecke operators, and using that concept, we could find infinite families of congruences modulo 2 satisfied by these two partition functions. Okay, so we just use the result of Ono and Taguchi on nilpotency of Hecke operators, and we find infinite families of congruences modulo 2 satisfied by these two families of these of Mex-related partition functions. So what we proved that for any alpha, positive alpha, there is some C1 greater than or equal to 0, such that for every D1 greater than or equal to 1 and distinct primes P1, P2, and PC1 plus D1, and all are co-prime to 6, we have that these values are always even whenever n is co-prime to P1, P2, and PC1 plus D1. So we have infinite example of infinite families of congruences which are 0 modulo 2. Okay, and of course this is expected because we already proved that this arithmetic density of these values is arithmetic density that these values are even is 1. So such congruences are expected, but it is really very surprising to see that for these partition functions we have a situation where we can apply the result of Ono and Taguchi. So I will explain how that result we can apply, and so what will be the associated modular forms for these partition functions, Mex-related partition functions. Okay, so similarly, for the other family of Mex-related partition functions, we have this infinite family of congruences modulo 2. And again here, we apply the Hecke nilpotency result of Ono and Taguchi. So now I'll quickly give the outline of our proof, how we have obtained the parity results, as well as how we have obtained the infinite families of congruences modulo 2 for these two families of Mex-related partition function. So idea is very simple, that what basically we do, somehow we relate the generating function of these two partition functions modulo 2 to some modular forms, and then we use a very deep result of Serre about the density or about divisibility of Fourier coefficients of modular forms, and then we connect the generating function of this partition function to modular forms, and then applying that result, we get the arithmetic density of our required partition function, or the Mex-related partition function. So we start with this Dedekind eta function, and then we define the eta quotient. So eta quotient is nothing but product of this eta function for fixing some n, and you take all the divisors of n, and then you consider this product, finite product, where r delta is some integer, so it can be positive, it can be negative, it can be 0, and this is called an eta quotient. And the standard eta quotient, just now Professor Ken Ono talked about that, is basically the famous Ramanujan's delta function. So this is Ramanujan's delta function, and this is a level 1 cast form of weight 12. Okay, so this is also an eta quotient. So you're taking here basically r delta to be 24, and all other, and all other things are basically 0. So only one eta function is appearing here. Okay, so so then we use this Serre's density result. What it says that when you have a modular form of positive integer weight k on some congruent subgroup of SL to G, and we have a situation where the Fourier expansion is of this form, where these coefficients, Fourier coefficients an, are algebraic integers in some number field. Okay, and then for every positive integer n, you fix a positive integer n, then what you get, that this an not equal to 0, an not congruent to 0 modulo m. So this set, this number of n, such that an is not congruent to 0 mod m, is nothing but big O of this x upon log x power alpha m. So there is some constant alpha m, such that you get this number in the order big O of this. And remember, these are algebraic integers I'm talking about. So here modulo m, I mean that is basically ideal. So this is a principal ideal. And when of course they are integers, then of course this is the standard, the congruence an not equal to 0 mod m. So now from here, what you get that when you consider the an is congruent to 0 modulo m, then you get that arithmetic density is exactly equal to 1. That means when you consider this an 0 modulo m, then this limit will be 1. So this set basically has arithmetic density 1. So this theorem basically says that these modular forms with Fourier coefficients, algebraic integers, then these Fourier coefficients are almost always divisible by any positive integer m. Okay, so we'll use this result, but for that, what we have to do, we have to basically get we have to prove that the generating function is related to some modular form modulo some m. Okay, so that m we have to choose, and we have to find what is the associated modular form. Okay, so we'll just use the definition of this generating function. So what we prove that when t equal to 2 power alpha, then you eventually get this eta quotient and modulo 2, and but this is not a modular form. This is not a modular form. So then we have to get some modular form so that modulo 2, that is related to the generating function t 2 power alpha comma 2 power alpha. So for that, what we do, we considered a function g alpha z. This is a eta quotient, and we can use the binomial theorem to prove that if we raise the power 2 power alpha to this function g alpha, then this is congruent to 1 modulo 2 power alpha plus 1. Okay, And then you use this eta quotient and you define this function h alpha. So for any alpha greater than or equal to 1, we define this function h alpha to be this eta quotient. And what we prove basically, this eta quotient h alpha is congruent to this this generating function. Okay, so this p2 power alpha, 2 power alpha, this modulo 2. So we have a situation where this generating function becomes a is nothing but h eta quotient h alpha modulo 2. So now what we have done is basically this h alpha. So our now aim is to prove that this h alpha is a modular form. Then we can use this sales density result. Okay, so this is what result that it says that we have proved that this h alpha is in fact a modular form for some congruent subgroup and even type character chi1. And interestingly, that this particular eta quotient has level n times, so this 9 times 2 power alpha plus 6, and this is very important because of this level, the structure of this level, we could apply the result of Ono and Taguchi on nilpotency of Hecke operators to establish the congruences satisfy these two families of Mex-related partition function. So quickly, I'll give the proof of this lemma, how we prove that this is actually a modular form. So it is very easy to find that the level of this eta quotient is 9 times 2 power alpha plus 6. And then this cusp of this congruent subgroup are represented by fraction C by D, where D is a divisor of this level and GCD of C and D is 1. Okay, and then this function h alpha z will be holomorphic at a cusp C by D if and only if this value L is greater than or equal to 0. So it's basically you have to evaluate now all the possible values of L. Okay, so that we do in this table. So we evaluate all the divisors of n times 2 power alpha plus 6. Okay, and then we find that these values are nothing but this type of values only you get, and then finally we evaluate what is the value of L. And from here you can easily find that L is greater than or equal to 0 for each divisors of the level 9 times 2 power alpha plus 6, and hence this is holomorphic at every cusp, and then it becomes basically a modular form. Okay, and then you apply the sales density result. So the Fourier coefficient of this modular form will be almost always divisible by m equal to 2. I'm assuming m equal to 2 because the situation we have is basically modulo 2 only. So here we have modulo 2. So modulo 2, this side all the Fourier coefficients are almost always divisible, and therefore these numbers are almost always divisible by 2. So this is the same way we can prove the density result for the other family. Now at the last 5 minutes, maybe I will just explain how we proved the congruences using the result of Ono and Taguchi. So this is one result we are going to apply, but this is just one part of the much general result of Ono and Taguchi. So what I am sitting here, the part we actually need to apply in our situation. So n is a non-negative integer and k is a positive integer, and chi is a quadratic Dirichlet character of conductor 9 times 2 power n. Okay, and then there is a integer c greater than or equal to 0 such that for every modular form, so this is important, this level 9 times 2 power alpha with integer Fourier coefficients, and every t greater than or equal to 1, we have that these TPs are basically the Hecke operators. So if we apply these Hecke operators, TP1, then TP2, then TP C plus T, then eventually modulo T power T, this this modular form will be 0 whenever the primes P1 up to PC plus T are co-prime to 6. So this is one particular case of a more general result proved by Ono and Taguchi on Hecke nilpotency, and we use this particular form of the theorem to apply in our situation. Okay, so we know that, so this is very important because this H alpha has this level 9 times 2 power alpha plus 6. Otherwise, we cannot apply this result. Okay, so we have a situation where level is exactly same what is required to apply the result of Ono and Taguchi. So using that thing, now what we have that H alpha, you have these are Fourier coefficients. I am writing A alpha, and then we know that modulo 2, so they are related to this this partition function in this way, and then you have this result of Ono Taguchi, and then this H alpha. Then if we apply these Hecke operators, so it will be 0 modulo 2 whenever these primes are co-prime to 6. Okay, so we're applying that result of Ono and Taguchi, we have this, and now what we do, you just apply the definition of Hecke operators, and then what will be the effect of these Hecke operators on the Fourier coefficient A alpha n of the modular form H alpha, and it basically we get that A alpha P1 up to product of P1 up to PC1 plus D1 times n is 0 modulo n. And now once we have this A alpha with this congruence relation, then you basically use this relation modulo 2. And so what we get basically, we get the infinite family satisfied by the Mex-related partition function P 2 power alpha, 2 power alpha. And exactly in a similar way, we can also prove that result for the family P 3 times 2 power alpha, 3 times 2 power alpha. Okay, so with this, maybe I will stop here. Thank you. And maybe I'll just mention about the references. So here, this is the article where Andrews and Newman, they introduced this Mex-related partition function. And immediately after that, the Silva and Sellers, they studied the parity of the partition functions P1, and P3, 3. And then whatever the modular forms on this Hecke nilpotency, we have used the results from this paper. It's a very big theorem, but we have only applied one part of this theorem by Ono and Taguchi. Probably this is the first volume of IJNT published in 2005. Okay, with that, basically we get the parity result for 2 infinite families of Mex-related partition functions. Okay, so with these words, I conclude my talk. Thank you very much for your kind attention.
Thank you, Rupam, for a nice talk. Are there any questions?
Can I make a comment combined with a question? Very nice talk, Rupam. This is stuff I thought about a very long time ago. And so listening to your talk was very exciting to me to remind me of some of the things that I used to think about. So in many of your theorems, you have a constant C1, the degree of no potency. So it occurs to me that you can actually compute C1 as a function of the parameters defining your Mex functions. So it would be interesting to say, in view of these parameters, you can choose C1 to be and just write down a number or a formula as a function of those parameters.
Okay.
But and the thing is, the C1 is the upper bound on the degree of no potency. So when you begin selecting primes P1, P2, P, etc., if you pick P1 to be in a certain arithmetic progression, sometimes picking P2 in another arithmetic progression automatically guarantees annihilation. So no potency is an upper bound for the maximum number of steps you can take before you annihilate a space. But before that, there's a whole network of lower lying combinations that annihilate forms. I sent you an email with an indication of how to do that. So you can imagine a situation where if P1 is a prime, which is 1 mod, I don't know, like 64, and P2 is congruent to something mod 64 that depends on P1, then TP1/TP2 automatically annihilates it, right? That's a more precise theorem.
Okay.
Do you see what I mean? Do you see what I mean by that? Yeah, those theorems are totally, I think, within reach.
Okay.
If P1 is a prime in some arithmetic progression and P2 is another prime chosen as a function of P1 in that, right? Then P1, P2, and must annihilate your form would be like a nice theorem. This is the kind of thing Frank was talking about with his PQ for Hurwitz class numbers. So by the way, these arguments apply there too. If you want to get large 2-power congruences for class numbers, it's not just cuspidal forms, it's also Eisenstein series and things.
Okay.
Okay, thank you very much for your remarks. I'll certainly look into your suggestions and try to answer.
I already sent you email. I sent you email.
Okay, I'll go into that. Yeah, thank you very much. Yeah.
Oh, I had one other comment. Arithmetic density 1, you can actually prove an asymptotic formula. So if instead of using Serre's theorem, which is the big O result, as a function of the parameters defining the Mex function, you could say the number of odd coefficients up to x is asymptotic to this constant times x over log x to the 1 minus a number, which you can compute. Okay. You can actually get an asymptotic. So it's like proving a prime number theorem.
Okay.
And while I'm at it, you might know about this famous theorem of Green and Tau that says primes form arbitrarily long arithmetic progressions. I don't know why. I don't know why no one has done this for coefficients of modular forms. But why don't you say the odd values of the partition function, even though we don't know that there are 50% of them, can we prove that various partition functions where almost all the coefficients are odd still form infinitely many long arithmetic progressions out of odd values? And the reason that people are interested in that is that it's hard to make density 0 subsets form arbitrary long arithmetic progressions. And it seems to me the odd values of a partition function which have these density 0 results are a very prime candidate for studying that.
Okay, thank you. Thank you, Kat, for your suggestions.
Any other questions? If not, let's thank Rupam as well as all of the speakers again.
Can I ask a question?
Sure.
Yeah, please. So I'm just wondering, Rupam sir, is there any possibility of proving these congruences using some other techniques like Q series manipulation, JTP, or anything similar to those?
Okay, so I mean this using the Q series manipulations, Da Silva and Sellers have already proved some congruences. But this is basically we have obtained some infinite families using the Haken-Nilpotency. So I don't know whether this what we have proved can be obtained by Q series manipulations. I have not looked into that.
Okay, thank you.
Okay. So let's thank Rupam and all of the previous speakers, Ken, Frank, Asia, and Peter, for nice talks and for making this symposium a success. So thank you all.
Thank you.
Yeah.
So thank you, everyone. And especially I once again thanks all speakers for accepting our invitations and delivering such a nice talk. And I also would like to thank Professor Atul for chairing this session. So we have come to an end of day 1 of the program of ICSFA 2020. Tomorrow, the first session will begin with at 10:30 Indian time. And in the first session, there are 4 speakers. They are Kalyan Chakravarti of Kerala School of Mathematics, India. We have Shigeru Kanemitsu, Kenkei University, Japan. We have Mahadev Naika of Bangalore University, India. And we have Yamar Rosengren of University of Gothenburg, Sweden. So these are the 4 speakers in the session 1 tomorrow. It will start at 10:30. And wish to see you all in the next session. Thank you, everyone. Thank you.
Thank you.